All right, good.
Hi everybody, my name is Nathan Kabza. I represent Flapping Wing Micro Air Vehicle. Our team leads are Lyndon Key, Mike, and Sam Hicks. So about Flapping MAV. We're an undergraduate and graduate research project started by Professor Taha. The project came from exploring the principles of vibrational stability in insect and flapping wing flight. And we found that through high-frequency flapping, a system can stabilize itself independent of control systems. So this could probably explain it better than I could. So as the system starts to diverge, by increasing the flapping frequency, it stabilizes itself. So some of the possible merits to this are in biomimetic micro air vehicles. So vehicles that could stabilize independent of flight controllers. So that was the original purpose behind the Flapping MAV project. So we started by modifying an existing ornithopter design, so these toy birds that you see, and the goal is to produce the vibrational stability in a system that can operate independently of flight controllers. So the project overview for 2018 is to explore the advantages of flapping wing flight over fixed and rotary wings for small scale use. The objective of our group is to develop and test the flapping wing micro air vehicle against rotary wing micro air vehicles. We want to mathematically model and simulate the system for flapping wing flight and design and manufacture new flapping wing mechanisms for efficiency and performance. So the breakdown of our team, we have the quad flapper team, the mechanical design team, and the simulation and visualization team. So each of those teams correspond to our goals for our project. So the quad flapper team, the idea was to apply this flapping MAV concept to something that we could compare and get usable data from. So instead of comparing a bird to a helicopter, so a single fixed wing propeller and a flapping wing system, we decided to use the quad flapper versus quadcopter. So we could get usable flighting. The mechanical design team is modifying this existing ornithopter design, so this gear mechanism that we have, and it's designed for horizontal flapping. So we have to optimize the mechanism to suit our parameters, which is high frequency flapping and horizontal flapping. And the simulation and visualization team is needed to model and simulate the system for flapping in flight. So to understand what's actually going on, we need to model the flapping MAV, the micro air vehicle, and experimentally visualize the flow through the bird. So the quad flapper team, some of our significant milestones this quarter have been to compare the quad flapper and quadcopter. So we have to ensure that they're ready for comparison testing. So we want to use the same exact system, or as close as we can get, so that we can use measurable and conclude. We want to conclude based off of our tests. So the idea is to make our systems as close as possible. Another goal is to construct an actual micro air vehicle, because these are using a bunch of different micro air vehicles. We're trying to modify the quad flapper so that it fits within the 15 centimeter requirement for a micro air vehicle. So requirements. The quad flapper and quadcopter must have comparable systems. So they have to be of a similar weight, dimension, center of gravity, and they have to have the same flight controller, motors, and battery, so that we can draw conclusions based on our test. So some of the metrics that we need are primarily in maneuverability and agility. So there aren't that many existing metrics out based on maneuverability and agility, especially for quadcopters. So one of the tests that we came up with was the roll test, which is the time to peak angular rate using a step input, attitude quickness, which is the ratio of peak angular rate to change in attitude, which is just the direction vector. The time to peak angular acceleration, flip recovery, how fast can a properly tuned system recover, and peak pitch angle, meaning the maximum pitch angle that the UAV can achieve before it starts dropping. And then our tiny flapper, our micro air vehicle must be less than 15 centimeters. So progress this quarter. So we have both our quad flapper and quadcopter built, and the weight difference is less than 0.1 grams between them. We completed our comparison tests and gathered useful data. The tiny flapper is completed and it flies. And we are semifinalists in the Cornell Cup, which was one of our goals. So the mechanical design team, their job is to fabricate optimized gear mechanism systems. So one of those gear mechanism systems is a two-stage gear mechanism with 2 wings and 1 motor. So in the drone that you see on the bottom right-hand corner, that's 4 wings, 1 motor, and passive pitching. So without going too deep into it, active pitching would mean the gear mechanism causes the wings to shift the pitch angle as it's going through the stroke. So it would, ideally we want a motion like infinity or a loop. So our goal for the mechanism team was to fabricate that this quarter. We have to decide and determine the optimal 6mm brush motors that fit within our gear mechanism, and we have to test and optimize the wings. So the requirements, so the 2-wing mechanism must utilize active pitching angle and using only 1 motor. The comparison test between the wings must include lift and frequency of each material with the same voltage input. So we want to test a bunch of different films and materials for our wings to see which one is suited best for our framing. And our lift test must use 1 degree of freedom to, a 1 degree of freedom pendulum to minimize variables. So the progress this quarter, we've tested 10 different wing types and determined a lift. Constructed a lab manual for construction of our mechanism, and we've completed the active pitching mechanism with higher stroking. So this is a detailed view of our mechanism. So the out-of-phase rockers are creating an active pitching angle for the wing. So it's not connected to a wing mechanism. So the simulation and visualization team is to model and visualize the system that we're using. So one of the goals for the simulation team is to compute the theoretical coefficient of lift with our flapping motion over time. So another experiment is to visualize the smoke, to use smoke visualization to gather data for our vortices. So the requirements for our simulation team, our CL bar, our average coefficient of lift must be a positive value. Otherwise, we're not using the correct parameters. So we have to constantly input and test different parameters to see what is giving us the correct coefficient of lift. The test rig that we use must use the 2 degree of freedom pendulum. Otherwise, it won't mimic the micro air vehicle in flight. The exit velocity of our smoke machine has to be very low, and we have to limit the amount of smoke that we use, otherwise our system will get all cloudy. So here's some visualization. So we completed these tests using a smoke machine, a nozzle, and a 2-degree of freedom pendulum. And after plotting the coefficient of lift for a bunch of different mechanisms, we got graphs that looks like this, but 10 of them. And after looking through it, the average coefficient of lift was a positive value, meaning our parameters were correct. And for next quarter, we plan on doing laser sheet flow visualization, meaning instead of having a camera or the smoke, we're going to use particles. So we're going to inject particles into a box and use a sheet of lasers to create a visualization for the particles in a single plane. And from that, we can do code to get flow fields and pressure differences. So our budget for this year, or this quarter, comes from our 189 students, 193 and 93 students, and a sponsorship from Northrop Grumman, and Professor Taha's fellowship money. So we have never gone above budget. Most of our purchases are significantly lower. The current equipment that we're using was purchased over spring and summer from competition money that we won. So next quarter we will be purchasing a laser for our laser sheet flow visualization, and those are between $5,000 and $10,000. So we have that covered. That is going to come from Professor Taha's fellowship fund. So most of our expenses, these are actually all our purchases for this quarter. Everything that we've done so far has been 3D printed or from previous quarters. So our resources, we have two 3D printers, a drill press, belt sander, bandsaw, Dremel, soldering equipment, heat gun, power supply, a large wind tunnel, smoke machine, various hand tools, and small wind tunnel for flying.